Okay, this is the next virtual lecture for EAPS536. The topic today will be the stratosphere and stratospheric circulation. The reading will be Vallis Essentials, chapter 12.4. So learning outcomes for today are to describe the basic structure of temperature and circulation in the stratosphere, as well as its seasonality, explain how the stratospheric circulation is affected by tropospheric eddies, and explain the two dominant modes of variability in the stratospheric circulation. So the structure of the stratosphere. So let's get started on that. So we're going to start off with the world in which if the atmosphere didn't move, what we call, going back to what we call radiative equilibrium, so only radiative heat transfer, no convective motions, meaning no movement of heat. Here's what the temperature would look like. So now notice on the y-axis here, so the x-axis is latitude from the South Pole to the North Pole. The y-axis now, we're extending much higher up, so 1,000 hectopascals at the surface, but we're going up now to 1 hectopascal at the top. So the troposphere is really the bottom third of these plots. And then the colors denote temperature, so reds are warmer temperatures, and this TE is the equilibrium or the radiative equilibrium temperature. In January and in July, and so note that summer and winter are noted in each of these hemispheres because that's really important. So the thing that hopefully jumps out to you a little bit when you're looking at these colors in the particularly the upper stratosphere is the pole-to-pole temperature gradient. So you can see in the troposphere, where we're used to things being warm at the equator and then cooling as you move poleward, and the stratosphere, particularly the upper stratosphere, but in general, that is not true. It goes the winter hemisphere pole is the coldest, and the summer hemisphere pole is actually the warmest. So you have the strong pole-to-pole temperature gradient. And so that warm summer pole is driven by summertime solar absorption by ozone. So we have an ozone shortwave absorber in the stratosphere here. So that's absorbing incoming solar radiation, particularly in the UV, and so warming up the air there. Meanwhile, on the winter side, you have zero absorption, you have polar night, so there's basically no source of heat, so it gets well, I shouldn't say it, no radiative source of heat here in general, and so things cool off very, very rapidly. You'll notice the story is pretty similar if you move over to July. So I've highlighted the arrows a little bit stronger in the winter hemisphere in July, so the temperature gradient, meridional temperature gradient is a bit stronger in the Antarctic winter than in the Arctic winter. Additionally, note that there's strong stratification here, so that's something that's really important in the stratosphere. We call it the stratosphere because it is stratified quite strongly, and so that means, as we'll note, that it's hard for air to move up and down. Vertical motions are quite strongly suppressed in the stratosphere. Which makes for relatively boring weather, we'll say. That's why our weather troposphere is interesting. So just a quick note here is this cold region. Note that the ozone hole develops here in the winter time, particularly in the southern hemisphere. We noted it's particularly cold at the South Pole. And the ozone hole develops here specifically in spring, so southern hemisphere spring, September, October. So the plot in the lower right just shows you the southern hemisphere ozone hole area from some different instruments for August, September, October, November for a few different years, actually. So just a quick primer in case you don't know much about this. Polar stratospheric clouds actually form at extremely cold temperatures that are particularly found in the southern hemisphere polar night. And these clouds provide a surface that catalyzes chlorine oxide production from chlorine-containing compounds, so those CFCs that have chlorine. And in the spring, the sun comes out, melts these clouds, and releases that chlorine oxide, that ClO, into the air, and that quickly destroys ozone. So it's the basics of the chemistry and dynamics of the ozone hole, and why it's found specifically in the southern or the South Pole springtime. Okay, so next let's compare, we're going to focus on January and compare our radiative equilibrium solution on the left with what's actually observed for temperatures and circulation on the right. So remember on the left we had assumed that there was no motion at all. So on the right now we have our real world where we have thermal wind balance, for example, that is imposed, and so there are relationships between temperature and circulation. We're going to go through those now. So again, summer's on the left, South Pole summer, Northern Hemisphere winter. And the contour interval here is 10 meters per second. So you'll notice, first and foremost, there's actually, if you look at the colors, is that there's overall a weaker pole-to-pole temperature gradient, a meridional temperature gradient. So we'll come back to that in a moment. But so to orient yourself, the contours, you see the tropospheric jet streams here near the bottom, in that bottom third of the plot in each hemisphere. So we've spent a lot of time talking about those. And you'll notice here in the wintertime hemisphere, that tropospheric jet stream actually has kind of an extension up into the stratosphere where winds then start to increase again with altitude. And so this is the polar vortex and the stratospheric polar vortex. We're going to come back to that term. The stratospheric polar vortex is a very strong wintertime westerly jet, where it's very cold right at the North Pole in the lower stratosphere. And then you'll notice something that's pretty remarkable is since the temperature gradient in the summer hemisphere is actually reversed, it's warmest at the pole and cooler towards the equator. That means that reverses from thermal wind balance are the sign of our wind shear. So the zonal wind has to be decreasing with height, and so you end up with a summertime easterly jet. So you have an easterly jet in the summer hemisphere and a westerly jet in the northern hemisphere, the winter hemisphere in the stratosphere. And so just overall to note, the weaker meridional temperature gradient that you see in observations indicates that there's a poleward heat transfer by the stratospheric circulation. So the fact that the real temperature distribution is not at radiative equilibrium, but has a weaker temperature gradient than radiative equilibrium is allowed if you have heat transport by the overturning circulation. So. All right, so let's move on to now the dynamics or motion of the stratosphere. So what makes the stratosphere move? So this is something that may not at all be obvious to you. We've thought a lot about the troposphere. So in the stratosphere, the thing to highlight is it's strongly stratified. Again, vertical motion in general is quite strongly inhibited. So N, our Brunt-Väisälä frequency, is 2 times 10 to the minus 2 per second, which is about twice as stable than the troposphere. A really important one, we spent so much time in the troposphere thinking about baroclinic instability. So in the stratosphere, that is not a significant driver of motion in the stratosphere. So we can go through a couple of reasons why, based on what you've learned before in this class. So the fastest growing wavelength for baroclinic instability scales with the deformation radius, this Rossby deformation radius, which is about 4 times longer or larger in the stratosphere than it is in the troposphere. So it's something in the order of 4,000 kilometers. And so just how do you get to that? So our Rossby deformation radius is the N times the fluid depth divided by F. And so in the stratosphere, H is something like 20 kilometers deep. So it's twice as deep as the troposphere. And the stratification is, like I said, is about twice as stable than the troposphere. So you can get a factor of 4 out of that. So F varies with latitude, so that obviously doesn't change. So you get a factor of 4 larger in the stratosphere. Second, as we learned, the ED growth rate for baroclinic instability, which is the fastest growth rate for instability, is significantly smaller than in the troposphere. So you have to go back and remember what's our equation for that. Sigma E is 0.31 times gamma, or lambda, which is the wind shear, over the fluid depth times H divided by the deformation radius. So we just thought about H and the deformation radius. That ratio is twice as small in the stratosphere than in the troposphere, given what we went through above. And then the wind shear varies quite a bit. It's arguably somewhat similar. But so again, you're getting a smaller ED growth rate principally from that H over LD factor. So the other key aspect is that there's no obvious change in the PV gradient to support counter-propagating Rossby waves like there is in the troposphere. So the mechanism by which instability can occur that we've talked extensively about in this class, it's not clear where that would exist. We don't really have the same surface and tropopause at Rossby edge waves or anything like that. So it's just not clear how that would actually occur. So in general, we say the stratosphere is generally baroclinically stable. So what does make things move? The primary driver for motion just comes from below. So this is Rossby waves and gravity waves, and particularly Rossby waves, which are generated in the troposphere in the same way that we've been talking about this whole time, especially recently. And then they propagate upwards and then break in the stratosphere. So we have a source of Rossby waves in the troposphere, and we have a sink of them in the stratosphere. So hopefully that's ringing a bell from what we've been talking about recently, as we'll come back to that in a moment. So the horizontal circulation in the stratosphere. So one really general way to think about the stratospheric circulation is that we said it's very strongly stratified, and so it behaves kind of like a purely two-dimensional flow. So what do we mean by that is we can go to the PV equation, so PV conservation equation, where there aren't really sources or sinks of PV, you just have PV that moves around. And so the PV equation is shown on the right. And so the third term for the PV is really the stratification term, this vertical term. And the key thing in that term is if n squared is large enough, you see there's a divide by n squared in there, this entire term can be neglected. And so you're left with basically absolute vorticity. It's basically an absolute vorticity equation with varying f. So that's where you have beta. So you'll still be allowed to have Rossby waves. So generally, this assumption holds for length scales smaller than the deformation radius. And so the key thing is that in the stratosphere, again, the deformation radius is a lot larger than it is in the troposphere. So it means it holds for a much larger range of scales in the stratosphere. So what does that translate to? And this is one way to visualize it that they go through in Vallis's book. So this is a polar projection. So the North Pole is right at the center. And you need to orient yourself. You can look at the black lines of the continents. So North America is in the southern part of this projection. And so what you're looking at is a tracer. You can think of potential vorticity since it's essentially conserved and moved around horizontally. You can think of it as basically a tracer. And so that's what's colored here. As a tracer distribution, the figure captions is in the Northern Hemisphere, lower stratosphere, in January 28, 1992, initialized by setting it equal to the PV field calculated from an observational analysis, and then advected for 12 days by the observed winds. So another way to think about this is the analog is your rotating tank experiments that you've done. So imagine that the idea is you're dropping blue dye near the cold North Pole, and you're putting red dye at the surrounding warmer latitudes. And then letting things evolve. And so what happens? So you've done this with baroclinic instability, and so this is a little bit different here. So in this case, what you're seeing then is in the blues is this cold northern hemisphere stratospheric polar vortex that's being kind of moved around. There's a sharp vortex boundary between the vortex and the fluid outside of it, and that actually inhibits mixing. So there's a general feeling that if you have the stronger the polar vortex, the harder it is to disturb it in some sense, because it's harder to cross that boundary and to mix across that boundary. You'll notice there's some undulations moving around longitude, essentially around the North Pole. So these are Rossby waves along the boundary. And then again, inside the polar vortex, you notice the colors are kind of uniformly blue. And so PV tends to get homogenized inside the vortex. So you'll end up with kind of a uniform PV field within this strong vortex. And then you'll notice generally outside of it, you get this, particularly near the boundary, you'll get this PV is being stretched and filamented outside, which is kind of a classic thing that happens in conserved 2D turbulent flows like this. So, okay, so that's a way to visualize the Northern Hemisphere polar vortex. And so what generates this Rossby wave activity? So you noted here there's Rossby waves. That's why it's not a perfect zonal flow here around the North Pole. What generates this Rossby wave activity? So we need wave activity to come from somewhere, and this is Rossby waves that propagate upwards from the troposphere below. And so note that only waves with relatively long wavelengths are actually allowed to propagate upwards. And it has to satisfy this very specific criterion that U is the mean wind speed. So we're thinking about westerly wind, so positive U in the troposphere. And so it has to be positive, but it has to be also not too positive. It has to be less than this criterion beta over k squared plus L squared. So if you go through and think about what k squared, long wavelength means small k squared plus L squared. So this implies that there's this filtering going on from this troposphere into the stratosphere, that only a specific range, it's basically a low pass filter of waves coming up from the troposphere, can make it into the stratosphere. So there's more information in chapter 6.4.2 of Vallis Essentials. We didn't actually get to that. It's actually a really important property for Rossby waves. So in general, we can just say that baroclinic eddies from the troposphere actually stir the stratosphere, which is pretty wild. So this is where baroclinic instability in the troposphere has effects that go beyond the troposphere itself, which is pretty cool. Okay, so we said Rossby waves propagate upwards from the troposphere and break in the stratosphere. So when we say wave breaking, we're thinking about wave activity dissipations in the same way that we talked about in the troposphere. And so that should hopefully bring a bell to you thinking about that's an EP flux convergence, which is to say a sink of wave activity. So we can go back to thinking about our EP fluxes and actually go back to our diagram that we brought up before. So first we'll just put up the mean zonal wind equation for the transformed Eulerian mean formulation, where we have our EP fluxes, our PV, our eddy PV fluxes at V prime Q prime bar. And so we're going to go back to the same figure. This is the same figure we looked at before. And if you had noticed, I didn't even reference it, but I had grayed out the stratosphere to focus on the troposphere. So now I'm removing that graying out. And so now you can see everything going up here to 3 hectopascals. So again, to orient yourself, the arrows are the EP flux vectors, and then the colors are the EP flux divergence. So blues are convergence, which is to say wave activity dissipation, which decelerates the flow, so a negative value for that V prime Q prime bar. And then the contours are the mean zonal wind. So first is to recall, so the easiest thing is to look at the arrows, is recall that Rossby wave energy follows these EP flux vectors. So you'll notice that the arrows generally in the mid-latitudes, we had looked at them in the troposphere, and now if you extend to the stratosphere, you notice that there's kind of this general upward motion all the way from the surface into the stratosphere. And specifically in one season, as we'll come back to in a second. But so generally, this is showing you that Rossby wave activity is just moving upwards from the surface within the troposphere, up through the troposphere, and then actually up into the stratosphere, which is pretty remarkable. So the blues here denote convergence, EP flux convergence. So that's something that technically decelerates the zonal mean flow. Zonal flow, I should say. And you notice that's stronger in the northern hemisphere winter, so it's shown on the right side, than in the southern hemisphere winter, shown on the left side. So something for you to think about. And so generally, these regions, the winter hemispheres in the stratosphere, is something we call the surf zone. It's a surf zone. Surfers like waves that break and like to ride the waves. There's lots of wave breaking going on there. And that's ultimately driving circulations in the stratosphere, as we'll get back to. You'll notice what happens in the southern hemisphere. Nothing is going on. There's no EP flux vectors getting in there at all. And you'll notice the zero, if you focus your eyes on the solid black contour, the thick one for 0, that's the line noting where there's a shift from westerly flow to easterly flow. So you mentioned we have easterly flow in the summertime hemisphere. So here the zonal wind is easterly, and actually upward wave propagation is not allowed. So we had just shown that constraint on where upward propagation is allowed, and we'd said that actually, if the zonal mean flow is negative, if it is easterly at all, you can't have any upward propagation, which is pretty remarkable. The waves actually just decay into those; they do not propagate through. So that's where you're seeing nothing there, which is pretty amazing. So most of the action in the stratosphere in terms of wave breaking and driving circulations is happening in the wintertime hemisphere. The summertime hemisphere is pretty boring in the stratosphere. Okay, so we talked about EP flux convergence, just as we did in the troposphere that drives an overturning circulation. We call that eddy-driven residual overturning circulation. That's going to be true in the stratosphere too. It was blue there as well, so it's a similar concept. It's driven by these breaking waves. And this is a term we call the Brewer-Dobson circulation. Some of you may have heard, which is really just the same, it's just the name given to the residual eddy-driven overturning circulation. And conceptually, it's exactly the same thing as we talked about in the troposphere. This is really just an upward stratospheric extension of the tropospheric residual circulation. That doesn't mean it's exactly the same. If you look through these plots, you'll see some differences, particularly in June, July, August. But conceptually and underlying physics are exactly the same. So what's shown here is in the top left is December, January, February, and then March, April, May, June, July, August, September, October, November. This is the seasonal mean transformed Eulerian mean stream function psi from the ERA interim. So this is giving you that residual overturning circulation. So you'll notice here, so just overlay some pink arrows so you have a sense of what air is doing. It's moving upwards in the equatorial regions up to very high altitude, very low pressure, and then moving poleward from there. So in the wintertime, northern hemisphere wintertime, it's generally a wintertime cell, you'll notice, because that's where the eddy, again, similar to before, you need that poleward residual circulation to have a Coriolis torque that can balance the weakening of the zonal flow by the convergence of the EP fluxes. So it's the same concept as last time. So you'll notice this is strongest in the winter hemisphere. Again, that's where when tropospheric wave activity is strongest. So this all comes back to you have stronger meridional temperature gradients in the winter time troposphere, and so you have a stronger jet stream. You have stronger eddies, meaning stronger cyclones, if you want to think about them, why we get nor'easters. And so for the same reason, this residual eddy-driven circulation, since these eddies propagate up into the stratosphere in the wintertime, that's when you see this residual eddy-driven overturning circulation signature be the strongest. So you see it as well in the southern hemisphere, June, July, August also. And so one really important thing to notice is that this circulation is actually bringing air into the stratosphere from the tropical troposphere. So you often might think of the stratosphere as being just this layer of air above the troposphere, but they interact. And this Brewer-Dobson circulation, this residual overturning circulation, is actually the mechanism by which air from the troposphere enters the stratosphere, and it does so via the tropical troposphere. So we can show this in another way. So a way to say this is this Brewer-Dobson circulation, or this residual circulation, is really a Lagrangian circulation. It's not an Eulerian mean. It's a Lagrangian mean in that you're following air parcels within eddies, for example. And this is true for the tropospheric residual circulation we talked about last lecture as well. So this means that the circulation carries tracers and pollutants, such as ozone and aerosols, with it, which is important for all sorts of things. So one way that's often used to show this is shown on the right is a plot of what we call age, the age of air. So this is a mean age of air in years, which may be a really odd concept. And actually all I'm going to focus on here is the black contours. The colors are but for trends in time, which you're welcome to look up on your own. But the black contours are the mean age of air. And the idea is that air enters in the near the equator at the tropopause. So you're going to say, as air enters there, let's pretend it's born. So it has an age of 0 as it enters the stratosphere. And then notice the contours of age move upwards. It's or tilt upwards. So air, you can get a sense of how air moves by thinking about how old it is or how long it's been since it entered the stratosphere. And so those red arrows are showing you that motion upwards over the equatorial stratosphere up to very high altitude, and then you have this gradual poleward transport, and this is all associated with this Brewer-Dobson residual overturning circulation. So just a quick note, this is actually fun fact. This is why large volcanoes in the tropics are often considered the most important source for sulfate aerosols in the stratosphere. It's why we care a lot about things like Mount Pinatubo in the Philippines or other tropical volcanoes, is those, when you have large tropical volcanic eruptions, the Brewer-Dobson circulation brings a lot of those aerosols into the stratosphere, and so and then transports them all over the world within the stratosphere. So that's why they can have particularly strong effects on the global climate. So. All right, so we're going to move on to one important concept that I want to highlight is this concept of polar vortex, because it's in the news a lot. It's a stratospheric versus tropospheric polar vortex, which is not at all the same thing. And really, it's the stratospheric polar vortex is the one that has meaning scientifically. Tropospheric has just sort of been introduced into the lexicon, the vernacular. So I'm just actually going to show you some figures from a paper that's actually a really nice and accessible paper by Waddell in 2017 in BAMS that's titled "What is the Polar Vortex and How Does It Influence Weather?" And so just the takeaway point here is that there are separate stratospheric and tropospheric planetary scale circumpolar vortices with differing structure, seasonality, dynamics, and impacts on extreme weather. So just going to go through their figures just to highlight this, is they have some nice schematics of here. When we say the tropospheric polar vortex, and I've actually added this is just the mid-latitude jet stream. It's not anything else. It just happens to be by thermal wind balance, the jet stream, which separates cold and warm air. And so in the stratosphere, and so it's shown here, the stratospheric polar vortex tends to be a little bit closer to the North Pole or to the wintertime pole, and is less wavy generally. So that's how that's schematically shown here. And so to show you some data, although hopefully you've already noticed this, we showed this before, so this isn't new, is they just have a nice colorful graph showing how the tropospheric polar vortex, there's really technically one in both hemispheres, whereas the stratospheric polar vortex is unique. It's specifically a wintertime stratospheric phenomenon, so it doesn't occur in both hemispheres. And so they also go through, just to give you a sense of thinking about visualizing variability or covariability of the two, is the top is showing the stratospheric polar vortex. The geopotential height is in colors, so it's a low at the center. And then it's also the PV, it's a high PV zone. Within the vortex, and so notice there's a very sharp gradient in the PV going from those reds in the middle to the greens and blues outside. And then they have a thick black line denoting the boundary, or a boundary of the polar vortex. And so that's in contrast to, you can do the same thing in the troposphere, look at geopotential height on a constant pressure surface on the lower left, or PV on a constant temperature or isentropic surface on the lower right. And so you'll notice again the difference in scale and also the difference in kind of waviness between the two. So. And then lastly, they just have a nice schematic. This is from 2014. There was the big January 2014 event that was called the polar vortex in the news, which was just a big cold air outbreak over North America. And so to orient yourself, you can see North America in the bottom of each of these figures. And this is each day where you're seeing in white. The white contour is the stratospheric polar vortex, kind of wobbling around, and then in black is the mid-latitude jet stream, basically. where what we called the polar vortex, or in the news was the polar vortex, you can see in the 5th of January in the top right corner, developing, is really just a trough. So it's just a trough in the jet stream that became called the polar vortex because it brought cold air with it, as being on the cold side of the jet stream typically does in the wintertime. So it's just a note. I'd encourage you to go and read that paper if you want to think a little bit more. It's written for a very general audience, so to understand the distinction between those two. Okay, so kind of the last component of this lecture is just to think about there's two dominant modes of variability in the stratosphere. And so the first one we're going to talk about is the polar vortex itself. So can variability in the stratospheric wintertime polar vortex affect tropospheric weather? The answer is yes. And so this is really kind of an emerging field of research, I would say, over the last decade. And so the dominant mode of variability in the stratospheric polar vortex is something we call sudden stratospheric warmings. SSW is commonly the acronym. And so this is, I'm going to give a quick intro, is generated by especially strong upward propagating Rossby wave activity. So we mentioned Rossby waves are propagating upwards in the wintertime hemisphere anyways, but you can have a burst of that, and that enhances the enhanced wave breaking temporarily weakens the polar vortex, and that can make it more susceptible to breaking down. And this is largely a northern hemisphere phenomenon, for reasons that you should start to be able to think about why. So to understand this, I'm going to show you a really nice movie. So we're going to show this nice movie from the Met Office that's going to go through in very beautiful terms how sudden stratospheric warmings work. All right, and then we have one final quick topic is a second mode of variability in the stratosphere that's quite important is what's called the quasi-biennial oscillation, or the QBO. We're going to have one slide on that here. Quasi-biennial is an oscillation almost every 2 years. Put it in normal human words. It's kind of a silly, ridiculous name, but something that occurs almost every 2 years. So what is this? So I'm going to show you here is a plot of the monthly mean zonal wind near the equator within the stratosphere. So you'll notice on the y-axis it's pressure from 70 hectopascals. I'm missing that to 10 hectopascals with the heights, approximate heights on the right side. And this is data from 3 radioson stations near the equator. And it goes all the way back to 1953. So each of these rows are just going in time for 20 years per row. And so you'll notice the blues are easterlies, or negative zonal flow at the equator, and then the yellows are westerlies, which is so positive zonal flow. So this is an oscillation of the equatorial zonal wind in the stratosphere, where it actually changes sign. So it switches between easterlies and westerlies. And the mean period is about 28 months. And the easterly phase amplitude is about twice as strong as that of the westerly phase amplitude. So the blues get bluer, or get more blue, versus the yellows are a modest yellow. You'll notice this is really a quite remarkably robust signal. It develops at the top of the lower stratosphere and propagates downwards. So you'll see in that propagation takes something like I guess like a year, I guess, which makes sense if it's about 2 years, almost every 2 years. And then it's dissipated, the signal is dissipated at the tropical tropopause. So it's really strictly within the stratosphere, though it does have effects on tropospheric weather that are increasingly being recognized. And so just in a quick note, what drives this oscillation? So it's again upward propagating waves, but in this case, this is upward propagating Kelvin waves, which are just gravity waves, but they happen to be long length scale gravity waves. Upward propagating Kelvin waves from the tropical troposphere. So again, we have waves that propagate upwards and then break, and so drive changes in circulation. So I encourage you to look up more about that if you're interested. It's just a very quick intro to the QBO. Okay, go to Blackboard to answer a few questions about this topic. Alrighty.